Assalamualaikum and greetings to all. My name is FIRDAUS bin Rasdan from UTM, and today I will present my technical paper which entitled Sustainable Surfactants for Enhanced Oil Recovery, Evaluating the Efficiency of Natural Saponin Extract. Okay, this is an overview of my background. So I'm currently studying as a second year of petroleum engineering student in University Technology Malaysia. Okay, this is the agenda that we will discuss today. We will discuss the overview, problem identification, proposed solution, conclusion, and also the reference included. So today, we are diving into a critical challenge the oil and gas industry faces, the efficiency of conventional oil recovery method. While this method has been the backbone of oil extraction for years, they have significant drawbacks. They often leave substantial amount of oil unrecovered in reservoir. This translates to missed economic opportunities and contributes to the depletion of our finite resources. Now, our focus is on a solution that not only addresses this challenge but does so in an innovative and sustainable way. Okay, surfactant flooding is widely used in the oil and gas industry due to its ability to reduce interfacial tension, alter wettability, improve sweep efficiency, and mobilize trapped oil, leading to enhanced oil recovery from reservoir. Nowadays, studies show chemical surfactant flooding has some several issues that need to be concerned. Firstly, the environmental impact. Chemical surfactants can be non-biodegradable and environmentally harmful. Toxicity concern. Some chemical surfactants may pose toxicity risks to ecosystem. Higher production costs. The manufacturing of the synthetic surfactants can be expensive. So the reservoir compatibility. Chemical surfactants might not be compatible with specific reservoir conditions. And lastly, the limited effectiveness. Certain chemical surfactants may not efficiently alter interfacial tension or wettability. So, our main solution is the natural saponin-based surfactant. This compound, extracted from sources like quinoa and Vernonia amygdalina leaves, present a fresh perspective on enhanced oil recovery. Okay, these are some benefits using the quinoa plant and the amygdalina leaves. So, firstly, which is the abundant saponin content. Quinoa seeds and Vernonia amygdalina leaves contain a relatively high concentration of saponins, which are known for their surfactant properties, making them conducive for enhanced oil recovery. The cost-effective extraction. The cost of cultivating and harvesting V. amygdalina leaves and quinoa plants for saponin extraction can be relatively economical, enhancing the cost-effectiveness of the surfactant production process. Cultivation viability. Quinoa and V. amygdalina is adaptable to different climates, allowing for cultivation in diverse geographical locations. Renewable resource. Quinoa is an annual plant enabling regular harvest and a renewable source of saponin for ongoing surfactant production. As a perennial plant, V. amygdalina can provide a renewable source of saponins, supporting continuous surfactant production. And lastly, the biodegradability. Saponins derived from quinoa and wheat amygdalina are biodegradable, contributing to the reduction of environmental impact during oil recovery operation and aligning with the industry's eco-friendly practices and minimizing environmental impact. Both figures shows on how to extract the saponin from both the quinoa plant and wheat amygdalina leaves. So from figure 2 is a schematic of the steps for processing the quinoa powder and the recovery of surfactant. First step, which is the processing of the quinoa seed coats, the extraction process using substrate extractor, and the rotary evaporator to separate solvent and recover the surfactant precipitate. While the second figure is the schematic experiment of extracting saponin from V. amygdalina leaves, which is the collection and washing of the drying Vernonia leaves, ultrasonic extraction, freeze drying, FTIR and HPLC, IFT and emulsion test, and lastly the oil displacement test. Okay, from the table, after conducting several experiments, we can see the table shown the IFT reduction, and the quinoa saponin achieved an IFT reduction of 8.7, corresponding to a reduction of 73.8%. Via amygdalina extract had a slightly higher IFT reduction, which is at the percentage of 71.4%. But both chemical spectrums also show high EFT reduction, but cannot compare to both the quinoa and also the amygdalina extract. And then the wettability alteration and emulsion stability. All spectrums show wettability alteration and emulsion stability, indicating their effectiveness in altering the interaction between water, oil, and road surfaces. For the environmental impact, both quinoa saponin and V-amygdalina extract are biodegradable, suggesting lower environmental impact compared to the chemical spectrums, which have moderate toxicity. For the economic viability and estimated cost, the quinoa and V-amygdalina extract are considered cost-effective with estimated cost of $10 and $12 per kilogram respectively. In contrast, the chemical spectrums NX610 and TR880 have higher production costs at $25 and $28 per kilogram respectively. So for the source, the natural spectrums are sourced from the quinoa plant and V-amygdalina leaf, while the chemical spectrums are synthetically produced. So based off the EOR efficiency and sustainability, all spectrums show high EOR efficiency, while the natural spectrums also be more sustainable. So in conclusion, the table provides a comprehensive comparison of spectrum EOR in terms of IFT reduction, oil recovery, environmental impact, economic viability, and more. It's evident that natural spectrums like quinoa and V-amygdalina extract offer a promising alternative with competitive performance compared to the chemical spectrums. So, in conclusion, we can see for the efficiency and sustainability, the results demonstrate that natural spectrums derived from sources like quinoa and V-amygdalina offer a promising alternative to chemical spectrum. They efficiently reduce interface tension, alter rock wettability, and stabilize emulsion, leading to enhanced oil recovery. So for the environmental responsibility, natural spectrum align with the industry increasing focus on sustainability and environmental responsibility. Their reduced toxicity and biodegradability make them an eco-friendly choice for EOR process. And the cost effectiveness, the experiment showcased the economic viability of natural spectrum. Their abundant sources and cost-efficient extraction method present a cost-effective solution for enhancing oil recovery. For the resource diversification, incorporating natural spectrum diversifies the industry approach to EOR, tapping into the renewable resources and reducing reliance on traditional chemical methods. And for the future implication, the success of natural spectrum in this experiment indicates a potential paradigm shift in the oil and gas industry toward more sustainable and efficient EOR practices. In conclusion, the experiment underscored the advantage of natural spectrum over chemical alternatives in terms of efficiency, environmental responsibility, cost effectiveness, and resource diversification. These findings have significant implications for the future of the oil and gas industry, emphasizing a transition toward more sustainable and innovative EOR methods. Okay, this slide shows the reference I used to make the technical paper. So that's all from me. Thank you. You can also contact me through my LinkedIn, phone, and email address. That's all from me. Thank you.